This is the first of a three-part video on indeterminate form problems. In this video, we will talk about quotient indeterminate forms, and parts 2 and 3 cover in separate videos. They cover the other types of indeterminate forms. I won't be talking about what indeterminate forms are or what L'Hopital's rule is in this video. I have a two-part video that discusses precisely those topics. So go ahead, take a look at those first if you need to before finishing with this video. Okay, the first problem in this video has to do with a fraction that you see here, and we want to take the limit of this fraction as x goes to 1. Notice that because x is going to 1, so does x squared. So plugging 1 for x, we get 1 minus 1, 0. And same thing down here. And so we have 0 over 0 expression. And that is in an indeterminate form. So we certainly can use L'Hopital's rule here, which says that this limit is equal to the limit as x goes to 1 of the derivative of the top divided by the derivative of the bottom. Taking the derivative of the top down here, derivative of x is 1, derivative of 1 is 0, derivative of x squared 2x, 1, 0. Now we end up with 1 over 2x. As x goes to 1, this is 1 over 2, or 1/2. And 1/2 therefore is the limit of the fraction as x goes to 1. We can also do this alternatively using algebra, because the denominator factors. And notice that in this case we cancel x minus 1, and we get the simple expression 1 over x plus 1. This is no longer an indeterminate form when we put x equal to 1. So the limit is just 1 over 1 plus 1 when x is set equal to 1. And that's 1/2. Same answer again. In problem 2, we want to find a limit of the same ratio as in problem 1, but this time x is going to 0. If we put an x equal to 0 in this fraction, we get the number 1. This is not an indeterminate form, so we cannot use L'Hopital's rule, but we don't need to. The number 1 is just the limit, and we found it by substitution. If we did apply L'Hopital's rule incorrectly, because it requires an indeterminate form, then we would get the wrong answer, because the numerator would have a derivative of 1, the denominator would have a derivative of 0, and this would approach infinity if x goes to 0 from the right, and it would approach minus infinity if x went to 0 from the left. So there would be no limit in this case. At least L'Hopital's rule would suggest that there is no limit, and that would be, of course, the wrong answer. In the problem 3, we have a fraction, x to the 9 plus 1, x to the 8 plus x, and we want to find its limit as x goes to negative 1. In setting negative 1, we see that we get 0 over 0, which is an indeterminate form. So let's apply L'Hopital's rule. Derivative of x to the 9 is 9x to the 8, and the derivative of the denominator is 8x to the 7 plus 1. Now if I put in x equal to minus 1 for x, and I calculate, I get that should be a plus 1. I get 9 minus 8 plus 1, or 9 minus, so the correct answer is actually minus 9 over 7, and that's the limit to this problem. In problem 4, we have the fraction or quotient sine of 2x over 3x. We want to take the limit of that as x goes to 0. This fraction turns out to be a 0 over 0 indeterminate form because sine of 2x goes to 0 as x goes to 0, since sine of 0 is 0, and the same and of course 3x goes to 0. Okay, so L'Hopital rule applies. We can use it and see what we get. Derivative of sine of 2x by the chain rule is cosine of 2x times the derivative of 2x, which is 2. And so let's write that here. Derivative of 3x is of course 3. Notice that if I don't have a 0 down here, so I'm not going to get an indeterminate form if I put, or even an undefined form if I put x equal to 0 down here in the fraction. Let's do so. Cosine of 0 is 1, so the answer comes out 2/3. It's kind of worth noticing that 2 and 3 are not special. If I pick any pair of non-zero real numbers a and b and carry out the calculation, the exact same calculation, I get this kind of a neat result down here. In problem 5, we are finding the limit as x goes to pi of sine squared of x divided by 1 plus cosine of x. This turns out to be a 0 over 0 expression because sine squared of x, which is the same as the square of sine of x, will go to 0 as x goes to pi due to the fact that sine of pi is 0. Also, cosine of pi is -1, so we get 0 divided by 1 minus 1, and that's how we end up with 0 over 0. So we can apply L'Hopital's rule, taking the derivative of sine squared x in the numerator gives us 2 sine of x to the power 1 times the derivative of sine of x, which is cosine of x, and that's our friend the chain rule. In the denominator, derivative of 1 is 0, and cosine of x has derivative negative sine of x. At this stage, notice that I can have a convenient cancellation, get rid of the sine of x. What's left is 2 cosine of x divided by 0 minus 1, or simply minus 1. Taking the limit of this as x goes to 0 is not going to be a problem now. Sorry, as x goes to pi, because the denominator cannot be 0. If we put in 0 for x, we get cosine of 0. And if we put pi, we get cosine of pi. And therefore, here it is. Actually, I don't need to do it. Here's cosine of pi. And cosine of pi is -1. And -1 times -2 is 2. And that's the limit in this problem. Right, x goes to pi. Don't know why I put 0 there. Using a similar calculation, you can figure out the limit of this fraction. And the answer will be different. Maybe you can pause the video and see what it is and give your answers in the comments. In problem 6, we are looking for the limit as x goes to infinity of the fraction or ratio or quotient x cubed divided by e to the x. We want to show that actually show that that limit is 0. The quotient is an infinity over infinity expression simply because x cubed goes to infinity as x goes to infinity, and e to the x, that's of course the same thing. So we can apply L'Hopital's rule. Derivative of 3x squared is derivative of x to the 3 is 3x squared. Derivative of e to the x is itself unchanged. Well, we still have an infinity over infinity. So we apply L'Hopital's rule a second time. Derivative of 3x squared is 2 times 3, 6x. e to the x unchanged. Again, as x goes to infinity, we get infinity divided by infinity. We need to apply L'Hopital's rule again. Derivative of 6x is 6, e to the x is itself. But now, 6, we can just plug in x, we can just take the limit as x goes to infinity. Because e to the x goes to infinity, 6 divided by that will be 0, and therefore that is the limit in this problem, just as we had claimed up there. In problem 7, we are taking the limit of ln of x divided by x. And of course, as x goes to infinity, ln of x goes to infinity, and we have an infinity over infinity indeterminate form. We can apply L'Hopital's rule. Derivative of ln of x is 1 over x. Derivative of x is 1. We can take the limit of this, which is just 1 over x, as x goes to infinity, and get 0. So that's the first limit in problem 7. In problem 8, we are looking at the quotient ln of x divided by sine of x minus 1. We are taking the limit as x goes to 1. Okay, as x goes to 1, natural log of x will be 0. Sine of x minus 1 will be sine of 0, and that's also 0. So natural log of 1 is 0, and sine of 0 also 0. So we end up with a 0 over 0 indeterminate form. We can apply L'Hopital's rule. Doing so gives us the derivative of ln of x in the numerator, 1 over x. Derivative of sine of x minus 1 is cosine of x minus 1 times the derivative of x minus 1, but that's just 1, so let's not worry about it. As x goes to 1, the numerator 1 over 1 is 1, and the denominator x 1 minus 1 will be 0, and cosine of 0 is 1, so the answer, the limit that we are looking for, is 1. In problem 9, and the last problem of this video, we want to show that the limit of this quotient here, or fraction, as x goes to 0 comes out 1/3. Well, of course, it's not easy to see how that happened, where that number comes from, but we won't worry about that since we can use L'Hopital. We want to see if we can use L'Hopital's rule. E to the 0, when x goes to 0, e to the 0 goes to 1, and sine 0 down here goes to 0. So we get 1 minus 1, and 0 plus 0. We get a 0 over 0 expression. So we can use L'Hopital's rule. Derivative of the numerator, derivative of e to the x is itself, and the derivative of 1 is 0. Derivative of 2x is 2. Derivative of sine x is cosine x. Now, as I insert x equal to 0, I get e to the 0, which is 1 on top. Cosine of 0 also 1. And 2 was there, so we get 1/3. That's where it comes from. And that concludes this video. I'll continue the problems with problem list with problem 10 in part 2, a separate video.